Christoph Stiller will talk about deep learning, behavioral safety, and motion planning. It's a very interesting topic. Thank you.
Thank you, Arnaud. I think I take this for the... Wireless today. I can speak without, but I'm not sure whether the recording works. Can you hear me at the back without microphone? Let me try this one. So that would not be better. That's better.
Yeah, no, it's not on yet.
Better?
Yes, please.
Yeah. Well, first of all, thanks Arnaud for the introduction and of course also for organizing this event, which is, at least for me, very beautiful here in France. I'll talk about motion planning and about quite different aspects, about...
It's a little bit tricky to hear you. I think it's not working, the microphone.
It is not
Put it louder.
Or maybe closer.
It is working, but it looks, I have to put it closer, thanks. Deep learning is of course technology which is getting more and more traction in automated driving. On the other hand, deep learning has at least one issue, and that is how to prove any properties of things which were developed with deep learning, and that's safety in automated driving. How can you use planning with deep learning and still prove safety? So behavioral safety will be an aspect that I'll be covering, and also motion planning. We see two of our vehicles at Karlsruhe, and unfortunately the building on the back is not our lab, but it's the castle of Karlsruhe. Yeah, so the overview, I'll start with some basic, with an introduction to the focus program on cooperative interacting automobiles, where many people here are actually from. Some constraints on motion planning. Constraints are basically drivability, so whatever you plan has to be a trajectory that a vehicle can drive. Integrity, you want to stay collision-free, basically, and that is particularly challenging if you consider that you plan for the future, and it means you have to know where will the others be in the future. Legality, so you want to drive more or less legal, and comfort, of course, is a soft criterion. So under those other constraints, you want to find a trajectory that is comfortable. We'll briefly review optimization based motion planning, but that was the main topic I had in the last summer school, so I'll just very briefly wrap up a few things from there. And this year, look more in probabilistic motion planning, look at markov decision processes, and particularly partial observable markov decision processes. And then I'll look at learning, reinforcement learning and deep learning. And finally, last not least, I would say, look at behavioral safety. We'll have a coffee break somewhere in between, and I'll also try to keep my time. Well, the German Science Foundation, Deutsche Forschungsgemeinschaft, has launched a focus research program, cooperatively interacting automobile, and that's people who proposed it, and it means that we have about 35, I believe, PhD students all over Germany, who are working together in all aspects of cooperative interacting automobiles. 35, I believe, were today, definitely. So we'll look at automated driving and car to X combination. So both are technologies that will happen in the not so far future. Car2X is already in vehicles. Automated driving is at least in some levels in automobiles today. And combining the two aspects means you're able to drive cooperatively among cars. And we know that being cooperatively in most situations, including traffic, is quite a good idea and makes your life happier, makes your life smoother. And we wonder how would that affect automated vehicles. Then several research questions are raised. So how should we interact? So how doesn't mean in particular the communication protocols. So we're not, I mean, these are also needed, but that's not the main focus. But what information should vehicles actually exchange, and how much should they trust in the information they receive? What should they send, and how should they use it to change their plans? What impacts would that have on traffic? So if you consider mixed traffic, where you have automated vehicles and still manually driven vehicles, what would happen if there comes a group of platoons, maybe on the right way of a motorway, with very narrow distances, and the manual driver can't go through that platoon, so he can't take an exit, for example. So it might be negative aspects on traffic as well, but of course we believe that the overwhelming effects would be positive. What kind of cooperation do we have? Vehicles today are cooperatively as well. Like if you work with pedestrians, if you drive through a city, you're also cooperatively today. So there's at least a form of explicit cooperation where you tell your plan, you really communicate via radio to another, or implicit cooperation. You can also communicate, for example, through trajectories that you're driving, or through the way pedestrians are moving. And how would that be in mixed traffic in particular? And we also look at the extreme case, the vision one day we'll have regions maybe on highways where only automated vehicles operate together. Well, that's how the automated vehicle will change. So we have a driver, we do the movements from bottom, we do the perception, we have a situation prediction, and intent recognition of others, and then we do cooperative maneuver, trajectory planning, and possibly if it's a level 2 or lower system, we have a driver. Assessment and plausibility checking is important for safety, and we'll have maps and other data that is stored in information based. So if we add communication to that, nothing really changes, just that you get more input, you get more output to others. So you get information from the senders of others, you exchange your intent to others, so the intent prediction will be much safer for others if you tell them what you're going to do. And also you could exchange trajectory plans with others. You could do crowd mapping in the database, such that the database is much more up to date, and it would be one provider asset. Types of cooperation we're looking at in that project is any cooperation between an automated vehicle and anybody else. So we do not, the only thing we exclude is a cooperation between two manually operated traffic participants, like between a pedestrian and a manually driven car. We don't look at that. But we do look at the interaction of an automated vehicle like with a pedestrian who might not communicate. Automated vehicle with another automated vehicle as the other extreme, and everything in between. We have 4 research fields, starting at the perception, so we want to do cooperative perception. There's quite a few people here as well. Situation prediction, I believe situation prediction is where the most uncertainty comes from. We have a research field on cooperative maneuver and trajectory planning, and on the data and information base, which should be done and updated in a crowd. Then, of course, we have system ergonomics. Quite a few people are here as well from that field. And then everything we didn't fit there is in the architecture and any other topic in the last field. Well, my talk today, as I said, will focus on motion planning. And motion planning simply has a goal. You get the pose of the vehicle. We assume we have a map. We have a goal where we want to go to. We know our vehicle dynamics, so we know what we could do, what we could not do. We have traffic rules and other rules that we want to follow, and we have a list of objects, including road objects. The plan then is to have some black box, and the output of that black box shall give me a steering angle and acceleration at every time in the future. Well, how do humans do that? That's the famous Rasmussen model, 3 levels. Go fast through that because I think most know that's on the lowest skill-based behavior level. What you do is you just get sensor information and you directly react to that without really thinking about what you're doing. A nice example is if you keep the lane on a motorway and you do something like that, you don't really think much about what you're doing, you just know you're keeping the lane. And it doesn't really go to it. That's a rule-based level where you recognize the situation that you know how to handle, you associate it with a way you have handled that situation before, and you follow the rules, so you follow the same behavior that you did successfully in the past. And an example for that is a pre-steering in curves. So if you look at driving beginners that drive a 90-degree curve, often have quite some problems because you have to turn the steering wheel so much. If you look at the skilled driver, experienced drivers, we don't have much problem because we know how to handle 90-degree curves. We could do it with closed eyes and then have a small, slight deviation, and the rest then can be stabilized on the lower level. Most important, most advanced level is a knowledge-based level where you really make plans in the sense, what would be if I would do this? And then you calculate different possibilities, so make a decision, so you then decide which of the possible options of action would lead to the best results, and that decision then will be your planning, and that is done for the navigation. So humans use all these levels simultaneously, and somehow we have to teach vehicles how to do that as well. Well, first of all, when we do that, we need constraints. Constraints that we need are basically coming from the car itself. So we know our car cannot do any trajectory that we could think of. For example, we cannot drive immediately to the side because we can only have front wheel steering typically. So drivability is one constraint. We have a vehicle dynamic model which constrains our motion. So it should also constrain our planning. We have integrity. So we don't want to collide with any static obstacles. We don't want to collide with any dynamic obstacles, and the latter are the critical ones because it's very difficult to predict what a dynamic obstacle will do in the future. And sometimes it's difficult to understand traffic rules because they're expressed quite vague. So that's why there's so many trials at court. So even if we know the trajectories of all participants in an accident, engineers cannot tell who's guilty. Only lawyers can do that. And there are some soft constraints. So you want to follow comfort. You want to have a high predictability yourself. So you want others in the traffic scene to understand what you are planning. Even if you don't communicate, it's a goal of me that others understand what I'm going to do. Like if I move across a pedestrian crossing, I want the pedestrians to see that, so I drive quite rigorously into into that zone, so that they understand this guy's driving, I better not walk. Or if I wait in front of the pedestrians, I clearly wait. So I decelerate early. Pedestrians see, okay, this guy's waiting, we pass, and at least then I don't have to wait as long as I would need if they would be uncertain and wait a little longer before they understand what I'm doing. And of course, cooperativity is a soft constraint that we want to do as much as possible. Let's start with the drivability given by the vehicle dynamics. We'll do that very short. There are several models. The simplest model that you can do is a mass point model. A mass point model dominated by the friction circle. The idea is very simple. It's a result from mechanics. It says if your vehicle is here and you're in the acceleration space, so you accelerate forward, backward, to the left and to the right, then the total amount of acceleration is bounded and by a constant, which means the acceleration is bounded by a friction circle, and so it's impossible to achieve any acceleration outside this friction circle unless you are colliding with some object. Then, of course, you can decelerate faster than just with your tires, but the friction between tires and road do not allow you to get out of the friction circle. So you can choose any acceleration inside the friction circle. Well, depends on your engine, of course, and if you look into it a little more closely, you'll find some areas where you cannot move to, but the friction circle is an upper bound, which is a very simple model. The next models come from neglecting or assuming tire forces. So you need to look at tire forces when you're driving very fast and when you're steering strongly. Otherwise, you can neglect them. Again, the result from mechanics is that it's your longitudinal axis of your tire. What it says is that in the beginning you have a linear tire force, and the tire force then gets into saturation. So when you start steering, you the tire force, which is exceeding and exceeding, the more you speed, the more you steer. But after some while, you get into saturation. If you turn your wheel too much, if your wheel slip angle between the longitudinal axis and the driving direction gets too large, you get into saturation of the force, so you cannot drive arbitrarily narrow curves. And when you have a longitudinal force as well, this saturation enters earlier. That actually is a consequence again of the friction circle kind of assumption. Typically, in vehicle dynamics, we assume everything is linear, so we linearize these curves, say for the front and the rear wheel, that the friction force, the force, lateral force, is proportional to the steering angle, which is true at least in some domain for moderate steering. Then there are two models coming out of that. The first one neglects all forces, so we assume we're driving slow enough so that we don't need lateral forces. That's called the bicycle model. In a kinematic case, so in the bicycle model, we replace four wheels with two wheels only in the center, so the red is our model, and that means that shows why it's called the bicycle model, because we only have a two-wheeled model, and it's a two-dimensional model, of course. Afterwards, you only look at motion in the plane, and for railroad it's good, and for moderate lateral acceleration, because you assume that the forces of the two wheels are about equal, so it's not happening that one wheel comes into the saturation of the lateral force and the other not. But you assume that both wheels behave in a linear case, in the linear phase, and then of course the sum of both is linear as well, and you can replace them with one other linear wheel. The kinematic model follows the Ackermann steering angle, which simply says, okay, that's your rear wheel. You have one point which is invariant to the motion, which doesn't move, and this point, of course, exists for every rigid object in 2D, and this point must lie on a line perpendicular to the rear wheel because the rear wheel is moving in this direction. Likewise, you assume from the front wheel that it's moving directly in the longitudinal direction. You assume that there is no lateral force, hence you have no wheel slip angle, hence you know that direction, and you draw another line perpendicular to that velocity, and you know that this point then is the invariant point of motion, so the vehicle moves around that point. This point would not move of the rigid body. And then, if you know that, you can calculate the motion of any other point, for example, for the center of gravity, and get the slip angle of that as well. Formulas on that example. The kinematic bicycle model is a little more complicated, but not much. It also assumes forces, in particular lateral forces, so you assume there is a wheel slip angle, like so if you're in a curve, you assume that the velocity and the longitudinal axis of a wheel is not aligned. So there is a side slip angle for each wheel, and then you have to look at the side slip force relationship, and you then have to impose the sum of all momentums is proportional to the inertial mass multiplied by the angular acceleration, and another balance equation would be the sum of all forces in any direction is the acceleration multiplied by the mass. And with that you can also solve for the bicycle model in the kinetic sense. So these are the two models that you can use, which look at least a little like a vehicle model, it's a bicycle model, as opposed to the mass point model, where you simply assume that you can have a mass point that can accelerate in every direction. So we already have three models for motion, and one of those is typically used in planning. The next constraints we're looking at is for collision avoidance. And in a nutshell, it says we don't want to collide with anything. For that, we introduce a configuration space. Configuration space for a car typically is in 2 dimensions. So we say the car is mainly moving on a plane. Then the configuration, the state space would be x, y, the position of the center of the vehicle, and phi, the heading angle, the angle of the vehicle. So we have r squared multiplied by 2 rotations, and so that's one angle. And in the configuration space of a robot, you might have the angles of all the arms that the robot has. So the configuration space is a set of all admissible states. So you can already see there are some states which are not admissible for that robot. In the free world, all states of the car would belong to the configuration space of this car, but that would change as soon as you have obstacles. So when we get obstacles, let's say these are some static obstacles, the configuration space gets smaller for our car. For example, if we know that our car is circularly shaped at the beginning, that's easy then. So that's our car. We could place a car here, but we could not place a center here. And we can easily see that when the car would touch one of the obstacles, then at the boundary of the configuration space, which is visible, and you can see that this extends the obstacles by the gray areas, such that the center of our car, or circularly shaped car, would need to fall beyond the black and beyond the gray area. If the car is not circularly shaped, it depends on the angle, how this configuration space looks like. So if we know that the heading angle is north, 0 degrees, we can do exactly the same and get that configuration space. If we turn it by 90 degrees, the configuration space is a little different. So for all orientations of our car, we get different configuration space. And if you look at that as three-dimensional space, we can see that somehow the configuration, the obstacles would look like that. A nice thing that actually Julius Ziegler introduced was to approximate a car. This is a silhouette of our car, and to approximate it by a couple of circles. So you say, okay, instead of proving that my car is collision-free, it's enough to prove that all those circles are collision-free. So in that case, 5 circles aligned. So that helps us to look in a 2-dimensional configuration space rather than a 3-dimensional configuration space. And we need to do 5 lookups in a 2-dimensional configuration space rather than looking at a 3-dimensional configuration space as before, and that's much faster because circles can be changed very easily. It is, as we can see, not tight. It would happen that the circle is actually a little overestimating the vehicle, but these overestimations, at least in our findings, are not very strong. If the car is moving, in practice it's even enough to check about 3 circles for the car, because the trajectory will make sure that you will not drive. Well, theoretically you could have a pole here and the check would say, well, that's collision free. And in practice, if there is a pole here, it would be a collision. But however, since the vehicle is driving so fast in longitudinal direction, it would be very unlikely that there's a pole here. You could check the final trajectory if you're cautious with a better approximation, but we never found that possible, that necessary. So for motion planning, this is how I would categorize it with different methods. Well, maybe the best known methods are discrete graph search methods. We have A-star, Dijkstra algorithm, and some other. We have roadmap algorithms which look at visibility graphs, and they basically produce a roadmap, a possible map of passes that we can go through. We have Monte Carlo methods, probabilistic roadmaps, rapidly exploring random trees. And then we have continuous optimization, in particular model predictive control. And we've seen quite posters yesterday, also quite some MPC approaches to motion planning. Potential field methods have been introduced to do motion planning, and some learning methods. And today I'll look a little at Monte Carlo methods and at learning methods, and we'll put my focus there. Trajectories. Well, in basic, what you have to look at is how do you define your problem. So if you have graph-based models, you try to put your state space in discrete space, so you have to discretize it in time, and also you have to discretize your action space. So you assume that you have discrete steering angles at any time. As that's quite successfully used in parking applications, for example, where the combinatorial aspects of motion planning are the most demanding ones. So in this case, the reds are the obstacles. You see the trajectory of our car planned from here to there, and just go force, back, and force to find a solution. We can prove it's the shortest path in this situation, and that would be difficult for a human even to find such a plan, which in some sense is close to optimal, and graph-based methods like A-star can prove to find that optimum infinite time, or to prove that there is no path from start to beginning, which would also be a good information, and that's quite successfully, and I would say more or less so. In contrast to that, we have continuous methods where we have an idea of how our trajectory would look like. Stay at the center of the road. Well, in that case, we have some obstacles. which would block that center trajectory, but at least we know almost how the trajectory looks like, and then you start to somehow bend this trajectory, variate it, to get a drivable trajectory for your car. And particularly MPC, quadratic programming, all those methods belong to the variation. So that's good if you know the structure. If you have a coarse estimate of how the optimal solution would look like. Continuous planning, some ideas of motion planning with optimal control. Optimal control says, okay, you have some control sequence, U star, so U star of t could be the steering angle and the acceleration signal that you provide to move it to the car over time. So U star is the optimum solution, and what you do is you minimize some cost measure, and this cost measure is integral over a cost measure at each stage of the planning. You have done some conditions. You say, okay, we want to minimize cost. Cost, in a nutshell, could be a square jerk, which would mean you drive very comfortably. So you try to avoid jerk. If possible, you drive with constant acceleration. And you have constraints. So you have a vehicle model which says, how does my state X transfer over time, given my input sequence, my command sequence U star. You have boundary condition that at time 0, where you start planning, the state starts at the position X where you just are, and you typically also have a boundary condition on the end, so X end is the position of the state where you want to finish after the planning horizon t, and if you put the planning horizon t to infinity, this boundary condition will vanish. And you would have some equality and inequality constraints, so you would have some constraints which must be satisfied. For example, here these inequality constraints could be, well, you have to drive left of the road boundary and right of the other road boundary. That could be expressed in such constraints. And then optimal control does the following. You have your starting state, your finishing state, you're looking at the trajectory, and you look at the optimal control sequence. You have some constraints. These inequality constraints could be, well, you have to not to pass through this circle, and you might not have to, and you might have to touch the cylinder, and that would be your constraints. And then you could try to variate the input such that the state evolves as you desire and you meet the conditions. That's optimal control. The main idea of optimum control is the Bellman principle, which says in an optimum control trajectory, each piece of the trajectory is optimal itself. And that allows for dynamic programming types of optimization. Okay, particularly easy those things become when you assume simple objective function, simple cost function, and simple constraints. So if, for example, you can assume that J is quadratic in the states, so what we typically have is something like square jerk criteria, and the constraints are linear, then you have a quadratic linear program, as we call that, that can solve this in very fast time. So there are solvers that I heard of. All solvers are in the region of some milliseconds in typical driving direction, and there are even solvers that work in microseconds domain if you consider that if the boundary conditions are not too difficult. So just for the constraints, that's the difficult part. But in industrial implementations right now, we do have some solvers which work in microsecond domain already on a vehicle computer platform. fast. Then, of course, the idea is to plan for time horizon. So you plan, let's say, for 5 or 10 seconds. But you don't apply this plan for 5 or 10 seconds because you don't know what others will be doing in 5 or 10 seconds. So you just replan at the tenth of a second. You only apply the first control input of your trajectory before you replan. So you plan to a much longer horizon than your sampling rate. That's the basic idea of MPC. Give you a very simple example. So suppose you only want to do lateral planning. So suppose you know the velocity of the vehicle, maybe because you're planning for a very short time horizon. In a very short time horizon, you cannot change the velocity too much. So velocity planning, that would be the state that you can plan is only the lateral position of your vehicle. You can further say, okay, my coast function at each time will be the deviation of my lateral position from the reference position. Reference could be the center of the lane or the center of the demanded directory, plus some other weight multiplied by the square of the deviation from the desired lateral velocity. Very often desired lateral velocity is 0. You don't want to move to the side if possible, not needed. And you could have the square acceleration to the side as a included in the cost function. With a weighted sum, you choose the lambdas to balance all these desired properties. So that's your comfort, your soft criterion. And then you might have very simple inequality equations saying, okay, you have a left border and you have a right border, and you don't want to collide. Don't want to lead that, and then you get a quadratic program that's extremely fast, even in MATLAB, where I did that. That's far beyond the second of computation. So that's my road. So the right and left boundary are the red and the left line for my car. So I assume a point shaped car, and then you can get the optimal trajectory. These are the two states, the three states where I already have had. These are the positions, and from the positions I can get the velocity and the acceleration at this time, and then you plan from this point along the road with constant velocity, and you get the trajectory like the black one. If you do the full linear quadratic programming, what people quite often start with is the first relax all the constraints. You would get this bluish curve, and then variate that. That could even be faster if you do linear system model assumptions, and if there is no obstacle in between the trajectories. So that is quite important. But of course, in practice, you don't start planning at a point where you already almost left the road. Yeah, so it's kind of an extreme starting position as well. With our Bertha car, we do exactly the same thing, just in 2 dimensions. So we don't plan velocity and path separately, but we plan that at the same time. And the first thing is, for that, we need to know where are the boundary conditions. So we have to look at where will other cars be in the next 5 to 10 seconds. So if that is a car, and that's the other car. So what we do is we first plan the boundary conditions by planning for others. So what we say is, okay, we assume that the black car will follow as good as it can its own lane. So if there are obstacles on the side, we accept that it might take a piece of our lane, but if there are no obstacles, we have a prediction that it will go towards the center of the lane. So we predicted Bertha with a couple of very simple deterministic predictors, and then we assume that it will drive all those trajectories at the same time. And from that we get boundary conditions. We know in the red time area, so the closed time area, it will not exceed this red polygon. And the next time area will not exceed the yellow polygon, the green and the blue afterwards. And then all we need to do is we need to plan a trajectory which in the red time area does not collide with the red boundary conditions. In yellow it doesn't collide with the yellow boundary conditions and so on. So you can see it's perfectly okay if our vehicle passes through here, because that means we'll be here in the blue time. But in the blue time, the black vehicle is already here, so we have no collision. So we share the space. We just make sure that we're not at the same time, at the same position than other vehicles. Then the planning looks like that. So we have the starting position, starting state actually, so we know velocity, we know acceleration, we know the time of course. So we have a 7-dimensional starting position, and we have a desired area where we want to land. After time t, we have obstacles, O1 and O2, which we don't want to collide with, whether they're moving or not. They're constraints. And then we say, okay, we optimize this function. The cost function is very close to what I had before. So we say, okay, the distance from the left boundary and the distance from the right boundary of the lane should be identical. So this term should be ideally 0. It means we drive in the center of the lane. Then we have another weight multiplied by the reference velocity, or velocity should be close to the desired velocity. So we have a road where we are allowed to drive 50 kilometers per hour. We want to drive this speed. The acceleration should ideally be 0. So if possible, we would never accelerate. The jerk should be ideally 0. And another thing that we found out is it's quite important to put a weight on the heading direction, the gear angle. So it means that we punish if the vehicle keeps changing its orientation. So we don't want to turn the orientation of the vehicle over time. That's the soft constraints. With that, we add some hard constraints. Hard constraints are drivability conditions, like the friction circle, or say the acceleration must not exceed a certain limit. And for Bertha, we don't take really the friction circle, or we take a smaller acceleration here than we could actually do. So we want to clearly stay in the linear domain. And we have outer boundary conditions, like the distance to any obstacles should stay positive. So we don't want to collide. That's the integrity collisions. Well, if you do 2D trajectory planning, the problem is you have a non-quadratic program that comes from different sources. One is that you have an X and Y coupling. So you have a non-linear coupling through the friction circle already. Also the vehicle model, it's not fully linear because the steering dynamics equation, they include velocity. So turn rate, of course, increases with the velocity you're driving, even when you take the same steering wheel position. So you have coupling between X and Y equations, and that is the difficult thing in 2D trajectory planning. That's why it's not a quadratic program. So there are many issues with that. If you apply a non-quadratic program like that to MATLAB, you can do that. Show that in a second. There are iterative solvers for that. They don't guarantee that you find the best solution, but in practice they're quite good. The issue is more that it takes a couple of seconds to compute it. So it's much slower, and that's the source of different approaches where you have some approximations. So of course also nonlinear vehicle dynamics would make the system to non-quadratic problems. Or if you have obstacles, right now we assume that the obstacles can be predicted before we plan. In practice, that's not the case. obstacles react to us. So we move differently, other obstacles will move differently as well, and they don't do that in a linear sense. So the prediction of other obstacles, that's another way, another reason why MPC is not perfect. So to avoid the much slower iterative solutions and the non-guarantee by the solver, what you can do is you can decouple path velocity. You first plan lateral, so I showed that you can solve it linearly, then you optimize longitudinally, and then you iterate that and hope that you converge to the right position. Here's some MPC results. So the vehicle, that's a black box. Planning in the time horizon, that came up to 3 seconds. So the color includes time. So you see here the circles of the vehicle approximated by 3 circles over time. We have a red light here. So the red light is like an obstacle blocking the whole road for a limited time. And we assume we can predict when it gets green. So as we can need to know the position and velocity of all obstacles, we also need to know in MPC the position of red lights, so the state of all red lights. And then in practice, so we have a static obstacle here, red light, which then vanishes at some point when it gets green. We have a pedestrian crossing, and it's in a way that the vehicle has to react fast with quite a fast speed on that course. And we have a dynamic vehicle coming onto us on the top, and we applied the MPC brute force planning of MATLAB. I'll try to get that moving. Let's try it again. So the vehicle actually exactly goes over the line when the traffic light turns green with some speed already, then it goes past the pedestrian, then it avoids this obstacle, and the plan already predicts where the obstacle will be and avoids it and keeps going. So that works quite nicely, and it also works quite nicely in cars. So this is a scene from Bertha, from the Bertha 2 in Heidelberg, a city we share with a tram and other vehicles on the road. Here we see our trajectory plan. This is where Bertha is. Constraints are colored as soon as they come from dynamic obstacles. And this is how actually Bertha has been driving through. It might have been worse to watch the tram, which of course goes in our lane because it does no lateral planning, it just drives and blocks our lane, and Bertha stops behind it. And then you see that we predict all obstacles yielding to many, many conditions, and that's easy to do it in real time. So we also see that the boundary conditions actually to the left and right boundary come from the map. Plus, since these are cities, you always have vehicles or other obstacles parked on the lane, which we then consider as obstacles. Another experiment from Freudenheim. I'll show you the whole Bertha band tour. This is like from Freudenheim, so we stop. For pedestrians and for turning vehicles. You get slower when the road gets narrow and the counter traffic, parked vehicles on our lane, which yield to the static conditions and the brownish color and the oncoming vehicles. These colors, boundary conditions. Daimler also has something like that in the F-Class series today. You can see some preliminary experiments at that. So they use a stereo camera, and they have a stopping and avoidance systems against pedestrians in their S-Class today and their E-Class as well meanwhile. So they predict with vision where the pedestrian will be moving, and if possible, they try to stop. If not possible, as you saw, there's a lateral steering. The steering, typically for pedestrians, something like 80 centimeters of steering is enough. So you don't really need to do harsh steering, but the steering must be very fast and very rigorous. And if you look at that, as soon as the car sees Hans, that's the name of this brave guy, keeps crossing the street, the vehicle evades as much as it can. Go to see a Daimler, this video, and of course it would not do anything like steering if there is counter traffic. 80 centimeters still mean you're still on your own lane. It doesn't leave the lane too often. But that's in series today, so you can see that such methods can be useful. Well, maneuver planning is something different. Right now in Berta, we always assume that we know whether we can evade a vehicle to the left or to the right, which is very easy for parked cars. If you have a parked car parked on the right, we say, okay, you pass by on the left if possible. That's a boundary condition. We don't try to pass it on the pedestrian sidewalk. So we have a very simple logic in saying, okay, if an obstacle in our lane is found on the right side, we try to find a trajectory on the left and vice versa. But we never assume that there's a pole in the center and you can either evade it on the left or on the right hand side. We never did that. What we actually did is we knew the maneuver. We knew in advance, as Arno has said yesterday, that the maneuver decision actually is a combinatoric problem which is not easy, particularly if you have many vehicles around, and there are many combinatoric solutions to a problem which might help. So one thing one could do is initialize an iterative trajectory planner with a maneuver planner. So first decide for the maneuver and then plan the best trajectory in that maneuver class. The question is, how do we find the best maneuver? And Arno gave quite some insight into how that works. We do it much less theoretically founded, I have to admit. So we simply take the map, the perception of the scene, and then, as I said, we predict everybody. So we assume we know perfectly what others will do in the future. We know their current velocity, so such a prediction is easy for 1 second. It is much more difficult if you extend in time, and particularly for pedestrians, even worse for children. Fortunately, actually, children are unpredictable. So it depends on what kind of object you have and what kind of time horizon you have for the prediction, how good we can be. Then you get all the maneuver variants that are possible. Typically these are not too many that we consider, so we try to consider 2 already, staying in the lane and making 1 lane change to one side at each time. But if you plan with 10 Hertz, it's enough to plan one after the other. Just keep the safe trajectory in your lane as long as you can drive, as long as you think that's the best. Then you do trajectory planner for some or all of the variants of the maneuvers. And then you can check which of the trajectories has the best cost, lowest cost, and decide for that trajectory. As a theory, we do that with the help of Philip Bender, who presented this as CIV2018 with a homotopy class. So these are vehicles, a red vehicle moving in time before us, the blue vehicle is moving in time before that vehicle with about the same speed, and there's an oncoming green vehicle moving in time in counter position. And there, in theory, there are a couple of maneuver variants. The fastest one is pass both vehicles, blue and the red and the blue one, before the green, and be back on the lane before that. The next variant, light blue one, is okay, pass the red vehicle before the green comes, move in between that narrow gap, and then overtake the blue after the green has gone. And the last variant that we consider is wait until the green obstacle has gone, so we're quite slow, stay behind the red vehicle, and then take over the two vehicles at last. And you could then compute trajectories for all those maneuvers and decide for which one you want to take. Well, that's an idea of optimization-based planning, and to me, the most problem with optimization-based planning is that you cannot model uncertainty too nicely. Well, you could say, well, if you don't know what others will be doing, why don't you model the uncertainty? And well, there are many sources of uncertainty. Uncertainty comes from actuation. So if we drive twice the same actuation on our vehicle, we don't drive exactly the same trajectory. And there, if we take feedback control, we can drive the same trajectory with about 1 centimeter, 2 centimeters. So that's not a major source of uncertainty if you have closed loop control. Uncertainty in sensing, that's larger. So particularly if we have vision and a long distance, we have quite some uncertainty in the range and the position of obstacles, and sometimes we don't even see obstacles at all, particularly in included regions. That's the largest uncertainty from perception, is that most sensors can have some included regions. So you cannot see a child standing behind a car, for example. But the most dominant source of uncertainty in planning is actually the uncertainty that comes from the future trajectories of others. So we try to predict others, or we don't know what they have kind of for an intent, so we don't know what they want to do and what they will do in the next seconds. And in particular, their action will depend on our action as well. And we do not yet consider that in MPC in our plan. Just as a question, you're in this situation, you're sitting in the black car, you're driving home maybe from here on the highway. Highway is fairly empty, you have one white car on the side. The question is, can we pass it? Now, would you pass? Would you not pass? Any drivers here?
Yes.
Tomorrow we have to solve
Yeah.
that problem. Quite often, yeah.
We should plan because we are on our lane, we have the right of way.
That's a good solution. So on our lane we have the right of way, so we can move. So the idea is, yes, we can. We predict the other, say the other will stay on his lane. So for 5 time steps, he's moving like that. We just predict, for example, constant velocity. What we do, we move in these 5 time steps like that, and we see we're collision free. So we're coming back home safely. Now, what happens with uncertainty? We don't know the velocity direction. It could be straight, that's our best estimate, but it could also be slightly to the side, and also the position of the vehicle might be somewhere in this uncertainty ellipse. Would you pass?
Yes.
It would still pass, okay? It could happen if you extend the uncertainty, you can predict with constant velocity. You see, it could happen that this guy comes from our lane. And then if we do that plan at that point, even if we would be on that other lane, we would hit somewhere with a vehicle, if that uncertainty is just propagated. It's even worse if we assume it can even accelerate somehow. So we don't do constant velocity prediction where we say, okay, it could accelerate to the left, to the right, forward and backward, and then you'll find out that the other vehicle will cover the whole space. So in total, this vehicle would have this uncertainty region in our time horizon. So you should not pass it. That would mean that a single obstacle would occupy a highway. That's like the railway systems where you have one train between Strasbourg and Karlsruhe more or less blocks the whole track over 100 kilometers. That's strange. So, well, you couldn't do it. You would still pass what you would say is, okay, I don't know the uncertainty, so I take one time step of MPC planning, knowing that in this time step I will not collide. And then, of course, the uncertainty decreases, or it moves forward, and it can keep going like that. And I have to admit, you have to assume that the other one doesn't make a sudden steering maneuver into you. So you have to assume that you'll tolerate the right of lane, respect the right of lane that you're having, and then you can pass by step, if the guy moves on the most likely trajectory. Yes, but what if this guy does not move on the most likely trajectory, but he takes one of the extreme trajectories that you have predicted? Then you would still be in collision, but no, you're still not in collision. What you would do is take a first time step, see what this guy is doing, and then react on that and decelerate, because then your prediction will be different. So what you do is then you decelerate again. You see that by the more denser vehicles and avoid a collision. So even for that crazy guy, you could avoid collision. So typically you're safe passing people on highways on another lane. Well, that's what we have known. I'm not looking at that, so I don't want to kill your coffee break. I'll rather look at macro decision process. So what you have to do is you have to plan, not predicting the worst, but considering the worst. Just make sure that even in the worst case, there's a plan B trajectory that you can follow and stay safe. And in the most likely case, you have a smooth and nice trajectory. So you have to just make sure that there is a safe trajectory under all expectable circumstances. What macro decision processes we think can do is kind of probabilistic planning, so you can assume uncertainty. Macro decision processes we've already seen here at the conference as well. For example, people from Berkeley do a lot of reinforcement learning for planning, and that is typically based on the assumption of a macro decision process. So macro decision process in a nutshell is the following. You have an action A which you take depending on state X, and the function determining the best action is called the policy P. Okay, so for each state, each position of yourself and the position of other vehicles, what you want to find is a policy that determines an appropriate action at each instance. Well, that's where reinforcement learning comes in. Reinforcement learning is, in the end, the policy learning. So you try to learn the best policy B. Well, which is the best one for that? You have a reward row, depending on the state and the action that you take at the time instance, and you don't want to maximize the reward you're getting now, but you want to maximize the reward that you get in the future. Where the Q function comes in, that's accumulating all the rewards over time until the time horizon T, and you want to maximize your action sequence such that you get the most reward. And the reward function then is something like the negative cost that we had in MPC planning. It means that, of course, you get a minus infinity reward if you have a collision, and then it means that you make sure that your reinforcement learner makes sure that you do not have a collision. Even if you assume very mild assumptions, so even if you assume that the vehicle model, the dynamic model, is deterministic, so we assume that our own model and the and models of others are quite simple, and you do coarse quantization of A and X, an exhaustive search is typically not possible in learning, but you have some Q learning to approximate typically somehow the Q function, or you approximate the value. Actually, one thing that I think is interesting is in a recent paper, I think it was last year, Charles Schwarz et al., these are the guys from Mobileye, Jerusalem University, including one of the authors also, Amnon Shashua, the Mobileye CEO. He says that we should have reinforcement learning to determine maneuvers, so to determine the homotopy, not to do the planning of the trajectory itself. The reason is that the state space of maneuvers is quite small, related to if you don't take all the combinatorics that were improved. But typically, in a driving situation, you only can stay on the lane, make a lane change to the left, make one to the right, maybe stop your vehicle. There are not too many maneuvers as compared to the state evolution over time, which is a very high dimensional space. The model gets a little more expanded if you go to POM-DPs, partial observable market precision processes, where you assume that the state is not given. So you do not know the state. You might know your own state, but the state in a market precision process for planning includes the position and velocity of all other vehicles. And of course, that can only be given with some approximation. Some vehicles, some traffic participants, the most dangerous ones, might not be visible. It might be a child behind a car, which you just cannot observe at any time. So you are not given the state X, but you're given a distribution of observations, O, given the state and the last action. So if you know where you are, where others are, you can somehow predict what kind of sensor signal could I get in such a situation. And you include sensor uncertainty, you can include model occlusions in the observation process and have a distribution there. And then the policy, of course, doesn't take state because that's not available, but the policy is based on the observation. So your action must be decided from the sensor measurements directly. Of course, you also need a state distribution. You need to know what is the next state, the distribution, the probabilistic distribution of the next state given the last state. It's easy for us, for our own vehicle, but as I said, the state also includes this position and velocity of other vehicles. That, of course, is much more difficult to predict. So this is a distribution rather than a deterministic function. Our part could be deterministic because our deviation from a planned trajectory is quite small. POM-DP planning, then I want to give just one example how that works. If you're interested, you can look at the papers which are typically displayed on the bottom. So that's work of Konstantin Hubmann. The idea is, first of all, the state space is the position of the ego vehicle and the position and velocity actually of all other vehicles. So we put position and velocity of all vehicles, but we assume that that path is given up to one decision that we assume vehicles drive more or less in the center of the lane if they can, but we do not know the path of others. So we do not know for another vehicle, like for the top one, whether it will go straight ahead, that would be the path R0, or whether it would take a right turn, that would be another path. So we don't know the intention, should we call that, of other vehicles. We only know how fast they are now and what position they have, but the intention needs to be estimated. States are not directly observable, so we cannot observe the intention. We can only guess the intention of other vehicles. And that, of course, in such a situation is a problem. If you're here, we want to make a left turn, we know our path, we know only want to go left. Then, if we assume the vehicle will take this action, we would just keep going because we have free lane. But if we consider this guy could move straight ahead, we would need to have consider constraints given by that other vehicle. So you could say, well, why not predict the intention? Well, even if you have a very good predictor, let's say you can predict 99% this guy will make a right turn because he decelerates. Maybe even he has set his turn indicator to the right. Would you trust that? I would say if I have a 1% probability of a collision, I would not take the risk. Because that's with high speeds, with 1% probability I have serious injury, and I'm guilty even in that situation. I have a traffic crash, so I can do that less than 100 times. And the probability then that I have one serious accident is quite high, so I don't take this risk because I travel 100 intersections, well, every month or whatever. So you cannot do that, even if you can predict with quite a high certainty what's going to happen. So you would need, taking a cost function, that with 1% you would have infinite cost, which would still be an expectation infinite cost for a collision. Instead, what you can do is you take observations. So you take the observations of yourself, that's quite easy, you know where you are, how fast you go, and of all other vehicles. Of course, we don't observe the intention, we see some velocity and position of other vehicles, and assume in that case that we have no measurement noise, because measurement noise is negligible against the noise in the prediction whether this guy goes straight ahead or takes a turn. So then we get a naive Bayes classifier, so we do that still, get the probability of turning and go straight ahead for each vehicle. And that probability will typically say something like, maybe if you're excellent, it can do something like 99 to 1% decide for one maneuver of the other car, but it never is certain enough so that we could trust it. And then what the system does in that situation, here slightly changed situation, is then we go to a planning tree which looks like that. We are right now in the state, and the red points here are the ones where the guy takes a straight road. The black points are situations where the guy finally took the right route. We say, okay, we take an action. That could be, in our case, the acceleration. So we accelerate. We don't accelerate. We accelerate fast, or we decelerate. And in all those cases, we get different observations. Because when we decelerate, other obstacles will stay farther away. Then, again, here in this tree, we would take another action, we would get another observation, and there you can see that this tree really grows fast. We again would plan with 10 hertz, 10 samples per second, 10 observations a second, 10 actions per second. We would have a huge tree, even if we only have 3 discrete acceleration possibilities, and not even lateral planning. And then what you can do is you can look at the branches of the tree, let's say after 10 seconds, and say we only go in a branch where we are absolutely sure the other car either turns straight and we are slow, or where the other guy makes a turn before, so we have no collision because he goes, and we can then go slower, but never the combination. And some results from that for the intersection that we had before. So again, here's our vehicle. I want to make a left turn. This guy goes straight or takes a right turn. We don't know. We've added another vehicle at some distance, 0, which goes straight ahead. So we have to merge into that traffic situation. And what the POMDP planner, the best solver, then does is the following. So you can see the discrete actions, acceleration here, no acceleration or deceleration, but no further options for our vehicle. The most conservative planner, if you would assume that you know the other vehicle takes the right turn, so you definitely have no collision. Sorry, if you go straight ahead, it's this one. So if you know there is a collision, it would be good. In that case, if you would predict that with an MPC, if you only have those reactions, that would be the trajectory that we would be driving. So we would slow down, come to stop here, even for a short time, let the other pass, and then accelerate again. That is a conservative plan, assuming the other will be on the collision path with us. So we decelerate, let him go. That means that then we cannot go before the green car, so before the oncoming car, but we even have to wait for that. The most progressive driver who would assume, oh, this guy will definitely turn right, would go the green path. So you would accelerate, he knows the other one goes. So if the MPC would predict the other guy is taking a turn, we don't have a collision, we follow that path, we can accelerate, move on our lane, and stay collision free. We don't know between those two extremes what will happen. And the MPC planner takes the blue route, so what it actually does, if you look at our classifier for the probability, in the beginning we say, okay, our classifier says it's about equally likely that the other car will take a turn or go ahead or go straight ahead. At that point, when he comes close to the intersection, the probability changes. In that case, the guy takes a right turn, and once we have the probability of 100%, that's actually when this guy already turns, starts to turn, we are certain and we can decide. So our macro decision process planner does the following: decelerates exactly along the conservative route. So it says, okay, we don't know whether this guy will go straight ahead, so we have to be conservative, because even here with like 5% probability we have a collision, and it only keeps accelerating when it also has a safe other plan. So what it does, it waits until the other car has decided. It makes sure that it's in a position where it doesn't stop when the other car has decided, but in a position where it's still moving and can do both trajectories. So it could smoothly still merge into the other traffic. It's by far not at zero velocity. So it can smoothly merge into the other traffic if the other car takes a turn. But if the other car would not have taken a turn, it would still stop the vehicle before a collision. So it does not predict really. The strength is not that it can predict what the other is doing, but it predicts when it knows the decision. POMDPs predict, they model at what time can I decide. They do not do the decision with a classifier themselves. That's very nice. It's the best maneuver planning that I have ever seen for such situations. It's the best maneuver planning in circular traffic. So we have a very similar situation where you don't know if somebody's in the circular traffic, will it take a deviation, will it turn out or not. What the POMDP planner does that is it moves with a reasonable velocity to the circular traffic and then takes a turn. We take a turn too at that point and have coffee break. We've looked at several motion planning procedures so far, which were either deterministic, like an MPC, or had a probabilistic model, but could have a deterministic brute force solver, even though we used Monte Carlo solvers to find the optimal solution. There's no proof for Monte Carlo solvers, of course, but we believe that in that case that was not the problem, and it was still too slow. Learning has raised a lot of interest in the past 10 years. Yes. Yeah. Okay. Learning, is that better? Yeah. To move it closer to the. Yeah. So learning has raised a lot of attention in the last years, particularly in perception, but also in planning. Deep neural networks are interesting. To show you one approach done by Andrea is done in the following. We first review Dijkstra's algorithm. So for those who are not familiar with Dijkstra's algorithm, most people actually will be, but in a very few seconds it works as follows. You have a starting goal, so you know you want to start at the green node, you somehow want to reach that goal, and you have a graph which tells what transitions from what node to what node are possible and which are impossible, and you have cost associated with each edge in the graph, and so you want to find the cheapest path from the start to the goal, adding all the edge costs on where you have to learn. You don't know, should you go such a path, or should you go such a path, or should you go downstairs, or whatever. And this is actually one solver that is well known for that is the A-star algorithm or D-star algorithm. So the idea is the following: you assign edge costs. Edge costs is the way that you say the start node can be reached with 0 cost, the distance is 0. Then you propagate at some cost. So if you say, okay, I can reach from the edge coast these 2 nodes. So the cost to reach these nodes are 2 and 4. Then you take the cheapest node. From the cheapest node, you say, okay, from this node I can get the fast. From that node, you can approach. You always take the cheapest node which hasn't been filled with green, so which hasn't been visited. You add from 4 plus edge cost 1 is 5, or here you get 7. Then you always look at the cheapest node that you haven't visited yet, that you haven't expanded yet, and you keep doing that until you reach the goal. So you get a lower bound for reaching the goal, but minimum node cost that you have so far, and which is not green. And once you reach the goal, once you expand the goal, you know that the minimum cost to the goal is the number which is in. So for each node that you expand, you know the minimum cost to reach. So Dijkstra keeps reiterating to calculate the costs to reach a node, the minimum cost to reach a node from the start. And then, in the end, you do get the cheapest path by looking back from the goal to the start, which nodes have you transited to reach the goal. So you then trace back the shortest path. Well, simple example, you have a start, you have the goal, and you then have transitions for the graph. These transitions will be like that, so you can traverse like that, somehow reach the goal, and to make it a little more complicated, you have an obstacle, besides that you're not allowed to touch, and then find the cheapest path. Quite an easy task that you see. Dijkstra really can guarantee to find an optimum path, and if there is no path, it can determine that there is no path. Well, how can you do that with CNN? With CNN, we know CNNs are extremely well suited for convolutions, and path actions are actually nothing else than a convolution. So what we do is we convolute the position where we are with a mask which looks like that. So if that is down, convolution mirrors the filter mask. So the output is that we get that position. So we say, okay, if you are here and apply this motion, we get this position afterwards, and we can do that by simple convolution. So going up is a filter mask, like that. Likewise, you can do go down, go left, go right, and everything else. Then we add the edge cost, for example 1, to that mask, and have our new mask. In practice, we not only do one action, but we take 4 actions, so maybe even here 0 action, where we say, okay, there we add infinity, because staying still is never optimum in an A-star algorithm or in a Dijkstra algorithm. So you do that for different actions, and you get different cost maps, and this cost map tells you how expensive is it to reach what map. So you do exactly what Dijkstra does. Then, having these cost maps, we can take the minimum. So we look for the minimum cost in all the 5 actions that we've taken, and we see there this is maybe how the minimum map looks like. So we do assign edge cost, we propagate and sum the cost, and we reassign the minimum cost exactly like in the Dijkstra. So the convolutional neural network, CNN, can do Dijkstra's algorithm. That would look like that. You have the cost map, you have the non-zero padding, you have to initiate with the static position, you have transition filters, so that's the motion actions. These actions then lead to cost maps. You add the transition cost for each of the 4 cost maps. In that case, get the cost per action here, that's the sum. And then you take a minimum pooling, which is also typical in convolutional neural networks. And the convolutional neural network can do fully Dijkstra, and you make that recursive, reiterating, and you replace the updated cost map in the beginning, and you keep going like that until you reach the goal. So you just have to wait until the goal node has a non-zero cost. Well, very nice. This is a cost per action. This is the important part of the CNN. So at that point, you take the argmin, you take the minimum action cost assigned for that action. Then, if you want to know the shortest path, these are the cost per action, you can reassign that by multiplying each current state with the cost per action, and then you saw what action was minimum. You have to flip the transition filters to go backward in time and get the next state, and that's how you can calculate the path. Well, so with the CNN, you can do path planning, and doing that, in our case, with 9 transition filters with a cost proportional to the distance it travels, so that would be square root 2. We start with a cost model as before in the Dijkstra toy example, and we have this start with such a cost map. Start, and we see how the cost map evolves all the time, where we always add the cost, infinity cost, for the obstacle region, such that we don't see the obstacle region, and that's a state transition that shows you from where do you go with minimum cost to each node. Well, then you reiterate the path, and you get exactly the same solution, of course, as you would get in Dijkstra, or if you would do a star algorithm. Well, very nice. I'll let that run once more. Anymore? Okay, I don't think I'll run it anymore today. So compare the Dijkstra algorithm to graph transversal with a node transition is faster. You don't visit each node like in the CNN several times. But once you have visited one node, you never visit it again. States can be updated selectively, so if you have a state and you can determine for each state you update it, whereas in the CNN you update all states which can be reached from one of the nodes that has been reached in the last step simultaneously, so you visit many states at the same time. But why would you do that? If Dijkstra has total less operational cost, why would you use a CNN for that? And the reason is you can learn, you can add some learning to the filters, you can add some learning to the cost map. And I will show you one example of that. So this is an example of mutation learning. So this is a Google Maps view from an intersection near our university. And what we did do is we stood with a vehicle, here's somewhere in the center, with a laser scanner, just looked at what are others doing, just observed all positions of cars and pedestrians, and you see this must be morning because people are moving from north to south, right to left. Few are also moving in the opposite direction. Some are turning into the university, very few are turning out, and we can see what others have been doing and what state transitions they have actually chosen. From this recording, from this knowledge of how do you behave at a spatial location near our university at that intersection, what you can try is you can teach a neural network. So we take exactly the same neural network that we had, that's a Dijkstra path planning algorithm. Now what we do is the transition cost we add. So for example, if we saw a vehicle, or if you saw no vehicle passing in a certain direction at a lane, which is typical because vehicles only move on one lane in one direction, because they're directional lanes, then we can add high cost to counteraction. So we add high cost to actions that we have never seen in the recording. So we assume that we want to make actions that others have taken lightly. And the more likely an action has been, the lower the cost that we add at that point for that action. So we have state-dependent, position-dependent transition cost, and we add these costs using some fully connected neural network from the aerial view using our recorded data. We look for, this is a path driven by human, naturally by ourselves, that we've recorded, and we have the cost map from the CNN. Looks like that. So there are some regions that are extremely high cost, so we never saw any car moving on the sidewalk here. We never saw cars moving on the traffic islands. There's, and of course, nobody moved through a building, through a library with his car. And we also know what actions were likely at what position. After our planning, the cost map looks like that, and then the minimum cost that the CNN then takes is from the same starting position, is just this trajectory, and we see the trajectory that we have driven and that the CNN is deciding for are almost identical, because most people stay on their lane and drive close to the center of the lane at that position. So one nice thing is with such a CNN, you can imitate you can include cost, which means that you imitate the typical behavior of something at a position. Next one is on Markov decision processes. So what we do is here we have pedestrians detected on the sidewalk. Then we get a cost map for pedestrians. Of course, the cost on the sidewalk will become very low. With some fully connected neural networks, this was extrapolated. There are obstacles like the parked cars. And these obstacles, of course, are very strong disabler of motion for pedestrians who never move through obstacles, and that can be used to, again, add to our neural network. So we increase the cost per action if it's a very unlikely action for pedestrian. And for Markov decision process, the terminology changes a little. So instead of cost, we use a value, do zero padding, because we want to have zero reward at the beginning. The transition filters are uncertain. We know that a pedestrian can not only do one motion, but it has some uncertainty, so we don't know what action the pedestrian will do. So there will not be one direct pulse, but a little more smooth, more blurred. Instead of transition cost, we have transition reward, and our cost map then becomes a reward map in the reinforcement learning framework, and we get an updated value. Now we iterate that, and we have, of course, to maximize the rewards, not to minimize it. So basically, the same CNN can be used for reinforcement learning, and that is the cost map and the detections. We teach the map network how humans behave, so we looked at a couple of humans for some time, what they would be doing, and we see that humans typically move straight along the sidewalk, parallel to the sidewalk, and that is how then our predictor comes up. So the net predicts pedestrians here, we have obstacles that most likely in some a second or two in time, that's a position where the pedestrian will most likely be. That's for the pedestrian where we really recorded where we saw over time. We see that this is the most likely path that a pedestrian will follow, and that's a heat map where we say, okay, how processable is the movement of a pedestrian? And we see that the pedestrian is influenced by obstacles, and the pedestrian wants to be parallel, or tends to be parallel to the road. With that, finally build a neural network which predicts the upper row, the intention of a pedestrian. The intention is a goal, so we say we keep a fixed date and time, so we say, like, where will the pedestrian be in 5 seconds? Use a CNN plus a position of our detected pedestrian, do a recurrent neural network, and then predict where the pedestrian will be at time, and we typically get discrete points blurred, like indicated there, where the pedestrian may want to go. So this guy may want to cross the road, or he may go along the road. Very unlikely that he will stay on the road for a longer time. And then, so that in the first network we determine the destination, the most likely destination of the pedestrian. Next network, we actually do the planning for the pedestrian, and it's a soft planning, so we don't take the argmax, but what we will do is a softmax operator, because we don't know which of the plans, which of the directions the pedestrian will follow. So we can plan simultaneously for all those directions with a single neural network, a fully connected layer there. Add then the topo map, that's our digital map, from where we feel action is typically on the sideway and parallel to the road, likely also perpendicular to the road in rare cases, but never on that long term. Then we have our planning network for each of the of those destinations simultaneously. I will get predictions, and the predictions will then be in a softmax algorithm, so we can predict what pedestrians are doing. As I said, planning the value iteration network with soft map, so if we have the coast map for each action, we plan for ourselves, we take the best action, the icons, we plan for others, take the soft maps. So we say, okay, we want a probabilistic detection. If you want to read more about the paper, the main author, Icarida, that was done in 2017, last year. And to close with that part, pictures of the main people, Icarida, who was heading that work, Yannick Wehl, and sein Tasch, the trajectory data, and Awaru as well. Florian Wirth did the destination prediction, Philip Bender, and Mr. Sobrino worked on that as well. Well, let's look at behavioral safety as the last point of my talk. That fast, we may look later. I'm not sure what will happen. Will it be a functional evolution when automated cars come into the market, or will it be a disruptive change? There are different paths to go from today to self-driving car center. One way that we see today, for example, this path is the one of where we do automation on dedicated roads and come to highway automation. Highway automation is announced by most car manufacturers for 2021, so in a little more than 2 years we'll see that you are allowed to read newspapers on upper class cars while you drive on the highway, but then eventually come to anywhere automation. Other people try to start with low speed, particularly some startups in Silicon Valley that do low speed driving, maybe build the last mile taxi, which cannot ride everywhere, but maybe just in cities and dedicated areas. And then hopefully you can extend these areas and get faster and faster. Both those ways will lead to an automated vehicle. Eventually, we don't know which of the ways will be the better ones or the faster ones. Maybe a mixture. Okay, we've seen the automation levels from Christina, even though she's not here yesterday, so I'll skip that, and I'll also skip the accident in Arizona. I'll skip that. That was the first deadly accident of a human. Just for those who have not seen that, this is the last few seconds of the vehicle driving, and as you can see, the vehicle did not even attempt to do any braking before it hit the pedestrian, and that was still in experimental trial. You can see the safety driver is not too observant until the crash actually is visible. 1 second before the crash, before the impact, you would see that scene from a dashboard camera with lousy quality, but lasers, radars, every sensor must have seen this pedestrian well before, and so I think these things will not be the problems of safety that we'll have in the future with self-driving cars, but many companies are far beyond such stage with their self-driving cars. Even our self-driving car would have seen that pedestrian in such a position. The safety goal is something very important that we have to state. The question is, what is safe enough? What is our safety goal? And there's a legal definition of risk and safety. In a nutshell, it says that risk is the potential of losing something of value. Sounds logical. And safety is the absence of risk. That's very, very difficult to get for me, because the absence of risk means safety is binary. Either risk is absent or it is present, which means that safety legally is a binary property of the system, which is not my understanding of things. In Bayesian risk, which is more my understanding of risk, risk is the sum of the probability that an event occurs multiplied by the hazard as the severity of that event, and to sum up overall possible events. That's the basic risk as introduced in probability theory. And that, to me, gives a nice idea how to, or one could try to make self-driving automobiles in the future. Could look at significant events, which basically are collisions. And in collisions, you could look at the most severe collisions. That's, of course, collisions with injury of a human. There is something like an abbreviated injury scale by medical doctors. So there is a scale that's AS level, and that AS level basically says how long do you need to keep somebody in the hospital, and will the injury be compensated after the hospital, will be cured after the hospital or not. And there are different scales, and with that you can measure the level of severity of an accident that involves injuries. In my following considerations, I will only look at fatalities, but of course severity and probabilities would be a vector, then adding all the injury scale levels to each other. If you look at fatalities in Germany, and I believe France and US are very similar. Well, the world, we know, we're 1.25 million people killed in traffic each year. That's what we accept today. So we are far from being a perfect system in traffic. In industrial countries, you drive about 2 times 10 to the power of 8 kilometers, so 200 million kilometers, and after driving 200 kilometers, you've killed one person. Or one person dies. So the risk is one death divided by 200 million kilometers. That would be the risk measure that we have today in conventional driving. And obviously we accept this risk level because we allow vehicles on the road. This changes a little if you go to German highways. The risk level is lower by a factor of 2.5. If you go, but in other areas of Germany than in cities, it's a little higher. So it's not constant, but it's always the order of magnitude that we have. And it's also the same order of magnitude, I'm sure, in France and in the US. It may differ in underdeveloped countries or in some other regions. But let's assume that's a risk of conventional driving. So what we want is that with automated driving, this number would be reduced significantly. Anybody an idea why significantly? Why would you accept a system which has 95% of the dead people? Would that also be nice to save 5% of the people?
Acceptability.
So,
Acceptability?
acceptability, yes. I would not accept a system which brings my life to danger with 95% of the average risk, because I believe I'm a better driver. In Germany, 95% actually of the drivers believe they're much better than average. That's a result from the German Automobile Association, who would ask people how good they drive and how good they relate their drivers, and more than 95% of all drivers believe they're much better than average. That's a good news. Well, we'll have accidents of conventional driving, hopefully less accidents of automated driving. There will be an intersection, but there will be this region where you kill people who would not be killed with conventional driving. The green is a nice part that's killed people who are saved due to automated driving. So you have to accept that it's not exactly the same people, it's not a subset of people killed by automated driving who are killed by conventional driving. So automated driving is a risky technology, risky in the sense that it will kill people, that we expect to increase safety. Sounds a little contradictory, but that's how it is. So we need to have careful safety before introduction. So one idea would be self-driving automobiles should have zero accidents. That would not be possible. So what I propose is to get something like a safety improvement factor, risk of traffic with conventional driving divided by the risk of traffic by automated driving. So how many people will I save? If the safety improvement factor is 1, we have the situation as today, at least in the number of people killed. And if the improvement factor is larger than 1, it means we save people. So how large does it need to be? 2, 3, 3.5, 10? So how large does the safety improvement factor need to be before we accept it? How would we prove that? Well, if you're involved in an accident, in 1.8 something percent, if you're involved in 1.8 something accidents, you're guilty once. The reason is very simple. If you're involved in an accident, most often you have 2 parties involved in the same accident, and only one of them is guilty. And there are some accidents that you do alone, and then of course you're guilty. So you have to be involved in a little less than 2 accidents before you're guilty. And that means if you count all accidents that a vehicle is involved in, you cannot improve better than that factor, assuming that other vehicles will still crash into you if you do nothing. It's very strange that some companies measure just the accident they're guilty in, and it seems that they're involved in far more accidents than normal, which indicates that automated vehicles somehow provoke accidents that human drivers would not provoke. So there are many cars crashing into automated vehicles. The automated vehicle is not guilty because the other car crashed from behind. The companies producing these cars say, you look, our car is much safer because it was involved in like 10 accidents and only 1 we were guilty in. So others are 9 times more dangerous than us. Well, that's wrong, because these cars are significantly involved in more accidents than humans are involved in total. So it seems they provoke accidents. So I think you have to look at all accidents, not just at the accidents where that the car is guilty. That's the discussion. Suppose you build a car with a safety improvement factor of 2. So you kill half the people when introducing automated driving. That's nice. We assume it's a Poisson distribution, which means you do an experiment, you drive 400 million kilometers, so double the distance of conventional driver that kills a car. So you would expect that a human driver would kill 2 people. Okay? So the Poisson distribution looks like that. Average human driver here, the yellow bar, kills 2 people, but it could, with the probability of, let's say, 15%, kill nobody. You could, of course, with another possibility, you kill 4 people, or even more in that experiment. That's the property of the Poisson process, that you say independent events over time. And lambda is just the number of expected accidents in that. If you get safer by 2, the Poisson distribution would look like that. In average, you only have 1 accident then. There's higher probability that you have 0 accidents. So you see clear improvement in the Poisson distribution, but you don't get this Poisson distributions. But maybe you get the expectation. So you may get 1 accident. That would be expectation of your car. And if you see that, you see that even after driving double the distance, you cannot say I have been safer, because with a probability of 15 plus 30, so almost 50%, the conventional driven car would also have 1 or less accidents. So if you're safer than factor of 2, a test of twice the distance of conventional driver is not enough to statistically prove that you are good with a reasonable confidence level. So if somebody would tell me, well, I have an automated vehicle and I'm confident with a probability of 0.5 that I'm at least as safe as a conventional car, I would say, well, you cannot introduce that because 50% means there's also a probability of 50% that you're unsafer. And that, of course, is not a significance level that's acceptable. You need something like 95, 99%, depending on legislation. And to finish that part, if you are 2 times safer with experiments, you see this curve is the number of counter experiments. You look at how much longer do you have to travel with a car which is 2 times safer to get a 95% confidence level. And you see that green curve, and it says that you drive 6 times 200 million kilometers to know with a confidence level of 95% that you are any safer than the car. You haven't proven you're 2 times safer, just proving I'm at least with that confidence level as safe as a conventional car. So you cannot prove anything with empirical tests because 1.2 billion kilometers, that's a couple of 100 times Earth's sun and back. So you do really exhaustive experiments. It's close to the driving capacity that the world has per year. It's in that order of magnitude. So you need to equip all cars, experimental vehicles in the world for 1 year to test this car and to prove with a confidence level of 95% that you are at least as safe as conventional driving, which of course is infeasible. The falsification is also not feasible. You also need in about the same order of magnitude of driving to be safe. So when we introduce automated vehicles, we will not know whether or not they're safer than our car, unless they're factor 100 or so safer. When we introduce a car which is factor 2 safer, we will not know whether it really reduces accidents or whether it may even increase the number of accidents. That's the message from that empirically. You have to model, you have to assume, and you have to believe in the introduction of this technology. So to close that talk at that point, I'll say when we introduce self-driving cars, we'll introduce technology where we believe it will be much safer than conventional driving, with the risk that we haven't proven that. That will be the dilemma of introducing self-driving automobiles. And so there are some strategies to still introduce. It would be bad not to introduce a better technology just because you cannot prove it. But if you have a strong belief in that, but as I said, there is no way to prove it. And that's something just to let you think about in the coffee break. I will stop my presentation with that at this time and be open for questions. Thank you.
Maybe before the break, we have a few questions.